Yeah, some people might have noticed it. The slides say Philipp Reisner, CEO LINBIT. That's not me. I'm just using his slides. My name is Robert Altnöder. I do work for the same company though, at least that is true. So the company is LINBIT. And we are working on a product that some of you might have heard about, maybe some have used. That is DRBD. It's a Linux kernel module. And that has had a focus on block-based replication of storage. And today's presentation is about the management layer that we're developing right now, which is called LINSTOR. That is a cluster management system that will allow you to manage DRBD resources, and in the future also resources that are not based on DRBD, so all kinds of storage technologies. A few words about LINBIT. LINBIT has been around for about 19 years now, started in about 2000 with DRBD as a master thesis project, and has since made its way mostly into high availability setups. That's how it all started for us. So most of the clusters that I was talking about were 2-node clusters traditionally, where you had one system where you would write some data in a high availability setup and you would mirror the same data to another system. That's where we originally come from. And everything is moving to cloud systems, virtualization systems, systems like OpenStack, Kubernetes, OpenNebula, if you've heard about those products. Maybe if, some of you use smaller setups, Proxmox as well. And all those projects and products are based on multiple node architectures. Those are all clusters. So that's where we're moving to, and that's the change that I would like to present today. Linux has a couple of storage technologies already built in, and that's what we use for DRBD. We've always used those storage gems and storage technologies as the backend for DRBD. So that's what we replicate, any kind of block device. Block device being, for those who are not too much familiar with Unix terminology, block device is anything under Linux that provides storage. Basically every storage device like SSDs, USB sticks, hard disks, even old floppies, all those storage devices show up as so-called block devices. And DRBD is able to replicate anything that is a writable block device. Some of those technologies, I'll just go over them quickly so that you know what's already available and what we basically use as the basis for LINSTOR and for DRBD. So we use those existing technologies to create backend storage for our replication product. One of the more probably widespread ones is LVM, Logical Volume Manager, which originally was implemented in AIX. It's a Unix clone, just like Linux, from IBM. And the implementation on Linux is not a port, it's a re-implementation. So it's written from scratch, but the idea is basically the same. You have a couple of physical volumes, again block devices. Those might be hard disks, those might be SSDs. You can also use other storage technologies that Linux provides, like a RAID system, and plug the entire RAID into LVM as a physical volume. And you can combine multiple physical volumes into a volume group. And on top of that volume group, you can create logical volumes. That's what you actually use to put your data on. And that's what we replicate. There's also a possibility to take snapshots of those logical volumes. The advantage here is that the logical volume can have a different size than the physical volumes that it is backed by. So it's very flexible. You can have like 3 or 4 physical volumes. You can create 20 logical volumes. You can only do one that is as large as 3 physical volumes. It will just spread out to all those volumes. Most people are probably familiar with that. And I'll always skip a few details because the original presentation was a bit longer. Those slides will be available for download, so you can look up all the details that I will skip. What's new and what's being used more and more is the thin provisioning feature. You can create a logical volume that is used as a thin pool for further logical volume. So you can have a mixed setup. You can create some logical volumes that are backed by actual storage, and you can create a thin pool and put logical volumes on top of the thin pool, and you don't have to have all the physical storage that you pretend you have. You probably know that. You can, like for example, if you have only physical storage of 400 gigabytes, you can still create a volume and pretend it has 1 terabyte of storage. As long as you don't write to it, as long as you don't actually fill it up, it will appear as if it was a 1 terabyte volume. And that's what many people do nowadays. They deploy storage, for example, for the virtual machines or containers. It looks a bit larger than it actually is. Then the RAID feature, you've probably seen that as well. MD, that's also in the Linux kernel. Software RAID, RAID level 0, RAID level 1, 4, 5, 6, 10. You can use that on top of LVM. You can use it below the volume group. So all those technologies are able to be combined with each other because it's all just block devices. Then there's also a caching layer. That's a bit of a newer feature, DM cache, bcache. And that's another layer of block devices, virtual block devices, more or less a filter where you get SSD caching for your hard disk drive. So that's a tiered setup. You have slower hard drives where your data, all your data is on. And the SSD cache will cache some of the data that is used frequently so that you have faster access to it. Deduplication is another newer layer that has been bought by Red Hat. It was originally a commercial project and has since been open sourced and put on the GPL by Red Hat. And it's another layer that you can combine all those layers to build your storage architecture, and that's what we make use of in LINSTOR. Now we're finally approaching the topic of replication and DRBD, and this is about iSCSI. DRBD is somewhat similar to that. With iSCSI, you have an initiator and a target, and there's even a list of different technologies and implementations on Linux. The current one being LIO, that's what everyone uses right now. And that is somewhat similar to what DRBD does. There's one slide in between for CFS on Linux, so I'll mention that real quick as well. And I heard there has been a problem in Linux 5, I think, license-wise, because one of the functions that CFS uses in kernel has changed to only being available to GPL code. It's already being solved by the CFS developers. It has been available in the Ubuntu distribution, so Ubuntu comes with CFS. Some of our Ubuntu customers use that. It works pretty similar to LVM if you look at it from a superfluous point of view. Has similar features. It can actually do a lot more things than LVM, but the basic idea of having logical volume management is pretty much the same. And now DRBD, we're going back to iSCSI. DRBD, you can think of DRBD as a RAID 1 system between two nodes, as if you had an iSCSI initiator and an iSCSI target, and your local disks are building a RAID 1 with your initiator side. And then your target basically does the same. You're mirroring from one node to the other node. It's like RAID 1 through a network. And as I said, it used to be between exactly two nodes, and that has changed since with DRBD 9. Instead of initiator and target, we call it the primary and the secondary. So we have at least one secondary node that replicates everything that the primary writes. And the interesting thing about it is that it is synchronous replication. So everything that gets written on the primary, everything that you write to the disk or to the SSD or whatever kind of storage technology you have below, is also written on the secondary node, and by the time that DRBD returns control to your application, so in more technical terms, as soon as the syscall has ended, the write syscall returns to the application, you have to guarantee that it has been written on both of those two nodes. That's the idea behind it. That's the default mode. You can also use it in an asynchronous mode where it'll avoid the network latency and make it less of a guarantee as to what's been written and what hasn't been written. So the basic idea is you have a primary node that has local storage, you have a secondary node that has a similar kind of local storage. It doesn't even have to be the same kind of storage. You could have an LVM backend on the primary side, and you could write directly to an SSD hard disk partition on the secondary side if you want. So it doesn't even have to have exactly the same configuration on all nodes. That's also what makes it interesting. And you can also create consistency groups. So we're not only dealing with volumes and replicating each volume completely separated from all other volumes, but there is also the possibility to create a resource that contains multiple volumes, and all those volumes are replicated across only one link. And a link in that case is just a TCP/IP connection. The idea behind that is that some data sets, like for example, something that a database writes, the actual database and the database logs, those need to be consistent, but you might want to have those on different volumes. So the idea with consistency groups is that whenever replication is interrupted because, for example, one of the nodes is not available anymore, might have a power outage, for example. The idea behind the consistency group is that both volumes stop at exactly the same point in time, so they are consistent. The database itself has the same state as the database logs. There is no time difference in those two volumes. That's the idea behind the consistency group. And then with DRBD9, DRBD has also learned to replicate to more than one peer. And now it's up to 32 actually. And that's probably a somewhat theoretical value because no one is going to replicate the same data 31 times. That's a bit of a storage overhead. Well, you have some, that's where the hum comes from. So normally what we see at our customer sites is 3 times replication, maybe 4 times, and very seldomly maybe 6 times if you have multiple data centers. The typical case is still 2 or 3 replicas. So you have a primary and 1, 2 secondary, something like that, per resource. So you can have multiple resources, and each of those resources can have multiple volumes. That's the idea behind DRBD. And another feature that only makes sense with DRBD9, it was actually possible in DRBD8 as well, but it didn't make a lot of sense with only 2 peers, is diskless nodes, or we call them DRBD9 clients. You can use that almost as a replacement for iSCSI. So the idea is that you can read and write from storage that you do not have locally. You only have the actual storage, the physical storage, on a remote node. So it reads and writes to the secondary, reads from the secondary, writes to the secondary, or actually all secondaries. And you don't need an additional layer like iSCSI to get your data from a storage node to another node that doesn't have storage. So we can basically replace the iSCSI layer by just using a DRBD9 client. And the same thing also happens if a disk fails suddenly. If you have a DRBD9 node that used to have local storage and disk fails, or the entire storage subsystem fails, it can just detach transparently, and all your applications still keep running as if there were local storage. It just writes to the secondaries and reads from the secondaries, obviously. And I skipped most of that. We have some additional features built in for clustering because most people obviously use it in high availability setups or as of today in cloud setups. So there are mechanisms for fencing, for quorum groups. Those are all to guard against certain cases where one of the nodes fails or the network fails. Split brain detection, you know, if you have two different forks of the data because you activated multiple copies without them being able to see each other, we can recover from that even incrementally. So we do not need a full resynchronization. Those are all DRBD features. And our further roadmap for DRBD itself is mostly focused on some performance optimizations. That's also one of the pro arguments for DRBD. It is very fast because it only deals with block replication. It doesn't deal with any file system details. It doesn't deal with any layers on top of that, like key value stores or databases or anything like that. So it is just another block device, a layer, like a filter. And we are building an erasure coding layer into DRBD so that you would not have to have full replicas of all the data. You could have multiple nodes and spread the data so that you have n+1 copies, things like that. Long distance replication is also something that has been available for quite a long time in DRBD, and there's an additional product to support that. And that's also new. It's currently in public beta test. There's a Windows version of DRBD coming up right now. It used to be a Linux product. It will be available on Windows as well. As I said, there's a public beta out by now. You can download that and just test it. And it is compatible with the Linux version, so you can replicate from Windows to Linux or from Linux to Windows. And it is still very tightly tied to the Linux code, so it is not a complete fork of our code. It still merges from the Linux version. So there's a compatibility layer on top of the Windows NT kernel that allows us to keep most of our other code pretty platform independent so that it works on Linux and on Windows. So all the features that go into the Linux version or into the Windows version will still end up on the other platform with only 1 day offset. If we do a new Linux version, you get the updates in the Windows version the next day. And there are some details. You can get those from the slides afterwards. Booting from WinDRBD and things like that. And then finally, what is all this LINSTOR talk about? That's the interesting question today. So as I said, we come from a high availability market originally where we only had 2 nodes. Now we have lots of customers that have cloud systems like OpenStack systems, Kubernetes containers, Open Nebula systems, Proxmox systems, systems where we need to plug our product into some other product like, as I said, OpenStack, so that you cannot even see it. With DRBD, in a 2-node setup, people just wrote a configuration file on the first server and copied it to the other server, and then they're good to go. That's nice if you have 2 servers and maybe 10 resources because you set it up once and then you're done. But if you have 100 servers and you have like 2,000 resources, then you probably wouldn't want to write all the configuration files yourself. You probably wouldn't even want to touch the storage system itself. You would like to have a plugin where you just select create new virtual machine in OpenStack or something like that, or you have it automatically deployed in Kubernetes. Just create a container that has a persistent volume claim, and it'll automatically create replicated storage for you. That is the idea behind LINSTOR. So what LINSTOR does is it takes all those technologies that I just briefly mentioned, like LVM, the deduplication layer, the Bcache, RAID, DRBD itself, and allows you to set up the system so that you can deploy storage resources that make use of those layers in different configurations completely automatically and plug that into some other kind of product like OpenStack or Kubernetes. So it builds on the existing Linux storage components, or if we use it on Windows in the future, then obviously on the Windows storage components, and there are not as many as the Linux ones, interestingly, and automates the process of creating a logical volume, putting, for example, an encryption layer on top of that, then putting a deduplication layer somewhere into the stack, maybe creating a RAID system out of it, and then putting that on one node and replicating it to other nodes that might even have a different storage setup. It's also built to be, to some extent, able to run multiple tenants. So it's, I'd rather call it multi-user capable. So you can define different identities and roles in LINSTOR and give them certain permissions, just with access control lists and privileges. And we have that's split. We have a discretionary access control layer and a mandatory access control layer. So you can more or less isolate some of those roles from each other by administrative action that they can't override with their access control lists, even if they own the object. And all of that is open source software, of course. It's under GPL, hosted on GitHub and also our own servers, but most people just download it from GitHub nowadays. So you can find the source code online on the LINBIT GitHub. Now let's look at some scenarios that LINSTOR makes possible. That is one possibility where you have a storage layer, a collection of storage nodes, and you have a collection of hypervisor nodes where you run your actual virtual machines. That's what you actually want to do. Storage nodes are supposed to provide storage remotely so that you can run the virtual machine as if the storage were locally available on the hypervisor. What we do in that case is we deploy the actual physical storage on 2 or 3 nodes depending on your setup. Most people do like 2 or 3 replicas of the data, and then we move a DRBD diskless client to the hypervisor that runs the virtual machine. So the virtual machine, from the point of view of the virtual machine, it seems as if there is local storage in the node. There's a block device that it can open and write to, but in reality that's on the storage nodes. And obviously you can easily move to another hypervisor by just moving the diskless client from one hypervisor to another hypervisor and migrating the virtual machine over there. And it still connects to the same storage nodes. For example, if your hypervisor fails, that would be one scenario. The other scenario would be one where one of the storage nodes fails, either temporarily because it has lost power, or permanently because the storage itself, the hard disk failed, the SSD failed, or it was lost in some kind of disaster. That is something that is completely transparent to the hypervisor running the VM, because the diskless client is connected to multiple storage nodes, so if one of them fails, it'll just use the other one. You don't even notice that locally. And then the more interesting setup is probably for most of the people who use cloud products, is this one, which at least the large companies call hyperconverged, where you have physical storage in the same node that is also the hypervisor that runs your virtual machines. And even in that setup, you could have local storage below your VM. You could also still use diskless clients. So the storage does not necessarily have to be on the same system where the hypervisor is. Normally it is, because that's a bit faster if you have local storage and you can read directly from local storage. So normally you would keep your virtual machine wherever your local storage of that virtual machine is. But there are also some scenarios that might be interesting. For example, if you migrate a VM, a virtual machine, might be because you want to rebalance the load. You have too many virtual machines on one hypervisor that take up too many resources, too much main memory or too much CPU time. Then that might be a case for live migration. So one possibility to do that is just to move the virtual machine to another hypervisor without having local storage there, because you can still do the same thing that it did with the split system where you had storage and hypervisors. You can still run in diskless mode, but what's interesting is that you can also put a new replica under a running virtual machine. So there is physical storage available on the hypervisor, and you're running a virtual machine on that hypervisor, but it doesn't have a local replica. You can transparently create a local replica. So even while the virtual machine is running on the diskless DRBD, you can basically insert the disk below the entire stack, and it will resync with the other replicas until it is up to date. And will even go into a mixed mode where it reads all the data that is already available locally from the local disk, and what's not yet available locally because it's still being replicated or resynced in that case will be read from the other nodes that have all the data. And then obviously you can remove the storage from one of the nodes where you don't need it, so that you don't create more and more replicas. You know, if you have 3 replicas, you can create a 4th replica temporarily, and when the resync is done, it will automatically remove the storage from one of the other nodes, so that you always have the same replica count. For example, 3 replicas in this. No, it's only 2 replicas in this scenario. So whatever your replica count is. And the idea is that all of this is done automatically. So there are commands for this in LINSTOR. There is a command to create a resource. There's another command to move a resource, to migrate it automatically, so that it'll create a temporary new resource, then do the resync, wait until the resync is done, and then remove the replica where it came from. And this is the architecture. This is how the system itself works. There are 2 components. LINSTOR has a control and a satellite module. Satellite module is running on every node that is able to provide storage or is supposed to consume storage by running diskless DRBD. So it doesn't have to be physical storage. It could be virtual storage, diskless. And there is at least one controller node, and there's only one active controller at any time. You could have standby controllers so that you can fail over if the controller node dies for whatever reason. Both components are written in Java. It's just a Java standalone process. It does not run in any kind of web application container or something. It's just plain Java. And it comes with an integrated H2 SQL database. That's where the entire setup is stored. But there is the possibility to use another database instead. So you do not have to use the integrated H2 database if you already have database servers somewhere. We also support Postgres, MariaDB, and DB2, the 3 databases that we support currently. So you could have some central database and use your company's database server, which makes failover somewhat easier with the LINSTOR controller, because it will just connect and reconnect to the database whenever it is moved. On top of the LINSTOR controller, we have all the, I'll just mark it up here, that's where all our infrastructure and cloud products plug in. That's on an API library layer. So there are API libraries available for LINSTOR that allow you to create plugins and drivers quite easily by just using the API library. That's basically a library that's object oriented, so you can create a LINSTOR resource, create some volumes, prepare everything, and then tell the library to just send that to the LINSTOR controller, and that will execute your request. The LINSTOR controller itself does that in a transaction-safe way. So either your transaction to create a resource or a resource with multiple volumes will either be accepted with all the volumes that you configured, or it will just roll back both in the database as well as in main storage, so there are no inconsistencies. And the protocol is also another interesting feature here. I don't know whether anyone is here who knew our previous product, which was only supposed to manage DRBD. It was called DRBD Manage, and used different protocols for communication between nodes and communication between DRBD Manage and the command line client. And that has changed in LINSTOR. There's only one protocol that is being used for all communication. So communication between LINSTOR and command line utilities, as well as communication between LINSTOR and OpenStack, OpenNebula, Kubernetes, Proxmox, and also communication between LINSTOR controllers and LINSTOR satellites, that all uses the same protocol, which is also just the TCP/IP based protocol with SSL if you run it in production. You could also run it in plain text, but the protocol is still the same. And what's coming up probably quite soon, it's currently being worked on, is an additional protocol. That's just a HTTP or HTTPS REST API that will allow you to basically make the same requests to the LINSTOR controller as the LINSTOR native protocol allows. So there will also be a REST API directly available in LINSTOR without requiring a web server around it or something like that. So the architecture of LINSTOR itself is modular in many ways. We can exchange the database layer, we can exchange the protocol layer, we can load different storage plugins. There are lots of possibilities, lots of plugins in LINSTOR. Even the APIs itself, all the functions that LINSTOR has, are just loadable, more or less plugins that plug into LINSTOR and do something. Obviously, data placement is interesting. You wouldn't want to select nodes manually if you have an OpenStack cluster of 60 nodes and you want only 3 replicas. You obviously have the problem of selecting which nodes you would like to have those replicas deployed. And that will be done automatically by LINSTOR, normally depending on how much space there is on each node. So obviously it would not choose a node that doesn't have enough storage to even create backend storage for your resource. But there are also additional features to allow you to control where resources are created. And one of our customers is already using that. I'll mention that in a minute. You can choose, and that's completely arbitrary, you can create any kind of tag on node that you want, that's completely under the control of the user, and then you can make rules based on those tags. Like, for example, put certain resources in a certain fire protection zone, or put those 2 resources on the same server, or put those 2 resources never on the same server, or not on servers in the same rack. Something like that. So you can form zones and create rules to tell LINSTOR how to deploy all those resources. You can also create some rules for network paths. There's the selection of the network path, because we allow to configure multiple network paths for different resources. You don't have to run every resource through the same network path, because you might have resources that are less important performance-wise, and you might have resources that need another level of performance, or you might have certain security requirements that require you to run those resources through different networks, things like that. It recently also supports DRBD's multipathing, and there are various possibilities to select a path for a resource. You can put a rule on the resource definition itself, or you could put it on the storage pool. So depending on which storage pool the resource uses, For example, the fast SSD storage pool, one of those storage pools might use a faster network than another storage pool that might be based on hard disks, for example. And I think that probably most people have already seen what it supports. So we have lots of connectors: Kubernetes, OpenStack, OpenNebula, Proxmox, Xen server. Those are all available. And what's new is that we also have a CSI plugin for Kubernetes. That's the most recent addition to the supported plugins, container storage interface. Currently both are available. You can still run the Flex Volume plugin or driver, but we're obviously recommending to move to the CSI driver. And that's our roadmap. The plan is to support setups that do not even use DRBD. So even it started as a product that was supposed to support automated configuration of replicated storage, but we'll also make it available if you just want to use LVM on lots of clustered nodes, or if you just want to build an MD RAID, or if you want to use NVMe over fabrics instead of DRBD, or you can even run mixed setups, obviously. And a lot of discovery for hardware, automatic hardware, software, volume group discovery. So we're trying to do more automation in the product. The REST API I already mentioned. Yep. And that's finally a case study that we're running with Intel, a pretty large company. I think you know that one. Intel has based its rack scale design, Intel RSD. That's a big project at Intel that is based on LINSTOR and currently also DRBD. It will move to NVMe over fabrics. And that has driven much of the development in LINSTOR due to the requirements that Intel had with selecting different network paths, different fire protection zones. So many of those features were driven by real life requirements that we had in the project with Intel. So many of those features have been tested quite thoroughly already, although we're officially still in the beta status. But as it has been used more or less in production already by some of our Vanguard customers. And that's about all about LINSTOR. I think we have a few minutes for questions, 3 minutes. So if there are any questions, then, and they'll also be available afterwards outside. Yes?
Is there any recommendation for the storage node about the setup of the disks? Or shall it be like with Ceph, just a bunch of disks, or shall it be like RAID disks and less replicas? Is there some recommendation?
Okay, so the question is whether there is some recommendation from Linbit as to how configure the backend storage that DRBD and LINSTOR uses. And I'd say in general, it depends a lot on what exactly your setup and your purpose is. But so if we know what exactly the setup is, we would be able to make some recommendation. But generally what we see and what seems good to us is, since you have, especially in those cloud systems, since you have rather cheap hardware with lots of cheap disks or maybe SSDs, and you're replicating to different nodes, and your entire design is based on the idea that a single node can fail or can even get lost permanently, it makes sense to just use a single disk or a stripe set, some kind of volume group, and that's what most customers do nowadays. In the high availability setups, we sometimes see customers that even do a RAID 1 mirroring locally and then replicate to another node. So that's 4 copies already. So all of that is possible. It depends very much on the setup and the purpose of your cluster. But what we see a lot is just a bunch of disks in various storage pools. And what most customers also like is the ability to use different storage pools, like either to just organize their data or make sure that one pool, if it overruns, so if it exceeds its storage capacity, it doesn't stop another pool from working correctly. Or because the pools have different backends, like a faster one based on NVMe and a slower one with large and cheap archive hard disks. Time's up. So I'll be available outside if someone has some additional questions. And I still remember I should ask the audience to please rate the talk on the FOSDEM homepage.